a tree that's used to store and look up information is called a search tree. A tree that is used to organize information with which we can perform various operations such as looking up, inserting, and deleting information. So let's define 3 operations on our ordered binary trees for this. A lookup operation, which returns the value corresponding to a key, k. An insert operation, which returns a new tree containing a new node with the pair k and v. And delete operation returns a new tree that does not contain the node with k, that removes this node. Notice that insert has to return a new tree. It cannot change an existing tree. This, of course, is because we're in the functional paradigm. So let me give you an example of this. Let me do something first here by hand. Let me create a tree here, which has some values in it. Key, for example, is horse. Value is cheval. And then the left subtree, well, let's go on. For example, the key is dog, and the value is chien. Okay, it has a left subtree. Key is cat, value is chat. And now we have the left subtree is a leaf, the right subtree is a leaf, and the right subtree of the dog is key is elephant, value is éléphant. Let me remove the accents because that would have me introduce quotes and it would be a little bit less readable. The left one is leaf and the right one is leaf. There. Now the right subtree of the original horse one has a key which is mouse, a value which is souris, a left subtree which has a key which is monkey, monkey, a value which is singe, and left is a leaf and right is a leaf. Okay, and now the right subtree here is a tree which has a key of tiger, a value of tigre, and the left subtree is leaf and the right one also is leaf. Now let me close all the parentheses, and now we've got our tree. Notice it's a lot of work typing it all in. Let me feed it to the system and look at it. The browser here, the font seems to be too big. Let me increase the size here. Let me reduce the size of the font so we can see the whole beast. Okay, here we go. So here you see the whole tree printed out nicely in the browser. Now let's try to do some lookup operation. If we want to look up, we have to travel down the tree. So for example, if we want to look up elephant, we go down and we compare with horse. So it's less than horse, elephant. That means we have to go to the left subtree. We compare elephant with dog. Elephant is greater than dog later in the dictionary, so we have to go down the right subtree. And then we compare, and then we find elephant, and the value is éléphant. Okay, now let's do a program to do that. Let me declare this function lookup, which takes a key and a tree and looks up. Now, what are the possibilities? Well, a tree is a recursive data structure, so we're going to go through a recursive here. So case T of leaf. Well, if the tree is a leaf, clearly there's nothing in there. So let me return an atom called not found. Otherwise, the tree is what? Well, it's something which is not a leaf, so it's tree with a key. Let me call it X, a value, call it V, a left subtree, call it T1, a right subtree, call it T2. And now we have to compare. So now I'm going to show you a little extra thing in the case statement. We can add a Boolean condition inside the pattern matching. So we have to now compare X and K. And there are 3 possibilities. X is equal to K. or x is less than k, or x is greater than k. Let me put these three possibilities here. Okay, so equal, less, and greater. Now let's fill in what the clauses. So if x is equal to k, we're in luck. We have found the value. It is found, and the value is v, which is the translation. Now we have the case x is less than k, or k is greater than x. If k is greater than x, or x is less than k, that means k is to the right. So we have to go into the rightmost subtree. So we have to do a recursive call, look up k into T2. And in the third possibility, if x is greater than k, that means k is to the left, k is less than x. That means we have to do a lookup in the leftmost subtree, which is T1. So you notice here the recursive structure of this thing. Let me put it a little bit like this to make it nicer. So here we have this recursive function which does the lookup. Now we can actually call it. Let me call it with the function example that I gave just before. Elephant T, and it will return found elephant. Now let me go and find lookup dog or cat, for example, T, and it looks found chat. Let me find another one, lookup lion, T. Well, lions are not there, so it says not found. So with this now, we can actually do efficient lookups. And notice that because of the decision we're making here, if the left and the right subtrees have similar size, that means they will both contain about half the nodes. That means each time we do a recursive call, we reduce the number of nodes that we have to look at by a factor of 2. And this is a very efficient way of doing a lookup.